Imagine building a computer so sensitive that even a tiny vibration, a stray photon, or a whisper of heat can destroy its calculations. That's not science fiction. That's a quantum computer. And the reason these machines need to be colder than outer space comes down to one simple word: noise. Classical computers are sturdy. Your laptop can run in a warm room, it can tolerate background radiation, it can survive being dumped on a desk. Quantum computers can't. Quantum computers use qubits, and qubits rely on quantum states like superposition and entanglement. But quantum states are extremely fragile. Heat is motion. At the microscopic level, temperature is particles vibrating, and vibration is the enemy. So let's slow this down. Heat isn't just warmth, heat is energy. It's atoms and electrons jiggling constantly. If a qubit interacts with that energy, even slightly, it loses its quantum behavior. This process is called decoherence. And once decoherence happens, the quantum computation fails. Not slightly, completely. So, how cold are we talking? Superconducting quantum computers operate at around 15 millikelvin. That's about minus 273 degrees Celsius, colder than deep space. Why that cold? Because at extremely low temperatures, certain materials become superconductors. Electrical resistance disappears. And more importantly, thermal noise drops dramatically. At those temperatures, the chaotic motion of particles slows down enough that fragile quantum states can survive briefly. To reach those temperatures, quantum labs use something called a dilution refrigerator. It's that chandelier looking machine you've probably seen in photos. Each stage gets colder as you go down. At the very bottom sits the quantum processor. It's not cold for efficiency, it's cold for survival. Without that isolation from heat, qubits wouldn't last long enough to perform even simple calculations. But here's what makes this even more fascinating. Cold alone isn't enough. Quantum computers also need vacuum chambers, electromagnetic shielding, vibration isolation, ultra precise control electronics. Because heat isn't the only form of noise. Stray photons, magnetic fluctuations, cosmic radiation, the universe is constantly trying to turn quantum systems back into classical ones. This extreme sensitivity is why building large scale quantum computers is so difficult. To create one reliable logical qubit, you may need hundreds or even thousands of physical qubits, all kept near absolute zero. Now imagine scaling that. The engineering challenge isn't just about more qubits, it's about protecting more fragile states for longer periods of time while performing more complex operations. And every additional qubit adds more potential noise. So, why do quantum computers need to be colder than outer space? Because quantum behavior only survives when nature is quiet. At room temperature, the universe is loud. At absolute zero, it whispers. And quantum computation happens in that whisper. The irony is powerful. To build the most advanced computers humanity has ever attempted, we first have to freeze them to the edge of physical possibility. If you found this fascinating, please like the video. And if you want more deep, clear explanations about quantum computing and emerging technology, subscribe and stick around. There's a lot more happening inside these machines than most people realize.